Hello everyone, a very good evening to all. I welcome you once again for this interaction session on atomic and molecular physics, which is being taught this semester by NPTEL with course code NUC 24 This is our 12th interaction session. Myself, Vivekananda Naik, I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So this is the Since this is the 12 interaction session, so we'll be covering a few problems that will be based on week 12 lectures of the NPTEL course Atomic and Molecular Physics. So this week was mainly the lectures of this week mainly covers the content of Raman spectra. So we will discuss briefly about the Raman spectra. Then we will solve a few problems which will be based on the Raman spectroscopy. So now, if you talk about Raman spectra, basically it occurs when a monochromatic light is incident on an organic liquid. So what is Raman spectra? So Raman spectra is when a monochromatic means light of a particular wavelength or single wavelength. Monochromatic light when it is incident on an organic liquid, then it was found that the light after the incident, the light which was coming from the organic liquid, the lights were at a frequency which was different from the incident frequency of the light. So the frequency which was obtained is not equal to the incident light frequency. So how it happens? So there is some change of energy between the molecules of the liquid and the photons, like the quanta of energy, light particle. So if you see, if the frequency of the emitted light is nu prime and the incident light is nu, then it varies or it differs with factor del nu. Now this factor depends whether the frequency will be more or less. So if when there is no absorption, like the frequency of emission is equal to the frequency of incident light is equal to the frequency of emitted light, then this is called as Rayleigh scattering. But when the energy is transferred from the incident light to the liquid or the organic liquid molecule, then the frequency will be lower. So this is the case of this line is called as Stokes line. And here the energy is transferred from light to liquid. And in the opposite case, when the light absorbs energy from the liquid, then this is called as anti-Stokes line, where the energy is absorbed from liquid to light. So if you see, the spectra will be like this. There will be at the central position, that is 0. There will be Rayleigh line, that is on the, the frequency of incident will be equal to the frequency of emitted light. And so this is in centimeter inverse unit. So the lights having higher wavelengths, these will appear at 6B, 10B like this. These are rotational Raman spectra, because you know B rotational constant, we have already discussed about it. So rotational Raman spectra. Then these lines are called as Stokes lines. These are called as anti-Stokes lines. Then it will be minus 6B, minus 10B like that. So how these minus 6b and minus 10b plus 6b plus 10b are coming, we will be discussing about it more in the upcoming questions. And also one more thing which is difficult in case of Raman spectra is, in case of Raman rotational spectra, the selection rule is delta J is plus minus 2. So the transition occurs from 0 to 2 or a transition occurs from 2 to 0. So these are a few things that we need to keep in mind while solving the problems related to the Raman spectra. Now let's discuss the first problem of the day. The question says the exciting line in a Raman experiment is 5465 Armstrong and Stokes line is observed at 5515 Armstrong. Then find the wavelength of the anti-Stokes lines. The options are option A 5416 Armstrong, 470 Armstrong, 530 Armstrong, or 5545 Armstrong. So these are the four options. Now what the question says, the exciting line in a Raman experiment is, the exciting line means this corresponds to the relay scattering because the light which was used to excite the molecules, liquid molecules. So this is given here as exciting line. So the wavelength of the exciting line is 5465 Armstrong, and the resulting Stokes line, which is obtained because you know the Stokes line, when the energy is transferred from the liquid molecule to the light molecule, then the frequency of the light which was incident will be increased, and that frequency is called as anti-Stokes lines. And the when the frequency of incident light is reduced, then it is called as Stokes lines. So here the Stokes lines is given. The Stokes line which was observed was at 5515 Armstrong. Now we have to find out the wavelength of anti-Stokes lines. So these are the four options that are given. I'll give you a few minutes to try this question. Then we will discuss how to approach this question. So now how we will proceed with this problem. Now we know the if you see the exciting line in the Raman experiment is 5465 angstrom. Now, if there is a shift in the incident light, then we can say the Raman shift, which will be given by del mu bar, which is the shift in wave number, is wave number of incident light minus wave number of Stokes line or anti-Stokes line, whichever it may be. But here, since the Stokes line wavelength is given, so we will consider Stokes line. So the incident, the difference between the incident wave number and the wave number of the Stokes line will give us the Raman shift. Now, this is the incident. This is incident line. This is Stokes line. Now, we know lambda I is given. It is 5465 angstrom. Now, nu bar I will be 1 by lambda I, which will be 10 to the power 8 divided by 5465 centimeter inverse, which is 18298.26 centimeter inverse. Now, similarly, lambda s bar will be 1 by lambda s, which will be again 10 to the power 8 divided by 5515 centimeter inverse, which is equals to 18132.36 centimeter inverse. Now you see the wave number of incident light is more and the wave number of Stokes lines is less. So according to our discussion also, the Stokes lines appears before the Rayleigh line or Rayleigh scattering. So the value of wave number for incident line will be higher than that of the Stokes line. So what is the value of Raman shift? This is Raman shift. So Raman shift is now 18298.26 minus 18132.36, which is equals to 165.9 centimeter inverse. Now, if we consider that this is the Rayleigh line, this is anti-Stokes, and this is Stokes. So the difference is delta nu bar. Again, here the difference is delta nu bar. So since Stokes line and the Rayleigh line have difference in wave number of delta nu bar, which is 165.9 centimeters. Similarly, the anti-Stokes line will be placed at the value of delta nu bar higher than the Rayleigh line at the central line. Then the wave number of anti-Stokes line will be nu I bar plus del nu. The incident is 18298.26 plus 165.9 centimeter inverse. So it will be 18464.16 centimeter inverse. Now, so this is 18464.16. This is 18298.6, and this is 18132.36. So the difference between them is 165.9. Here also difference is 165.9 centimeter inverse, centimeter inverse. So now, but here in our question it says what is the wavelength of anti-Stokes line. So how we will find the wavelength? Now the wavelength of anti-Stokes line is 1 by wave number of anti-Stokes line. It will be 1 by 18464.16, which will be 5.416 into 10 to the power minus 5 centimeter, or 5416 into 10 to the power minus 8 centimeter, which is 5416 angstrom. So the wavelength of anti-Stokes line is 5416 angstrom. So this is the correct answer. Now if the options you see, option A is the correct option. Now how did we solve this problem? And the question it was given that the exciting line in a Raman experiment was 5465 angstrom, and the Stokes line is observed at 5515 angstrom. Now we already discussed, if the light if the energy gets transferred from the photon to the liquid, then the frequency of the incident line will be lower. And since the frequency of the incident line will be lower, the wave number will be also lowering, because uh, frequency direct proportional to the wave number. So here we know the exciting line has the wavelength of 5465 angstrom. So from that wavelength we deduce the wave number. Then from that wave number we have two wavelengths, so we will be having two wave numbers, and the difference is known as the Raman shift. And then one is less than the incident light, another will be higher than the incident light. So the difference we got, we will add that difference, which is the Raman shift value, to the incident line. Then we will get the value of the anti-Stokes line. So we first, so since all these are calculated in wave number unit, so first we calculated the wave number corresponding to the anti-Stokes line, and then from that wave number, 1 by wave number will be the wavelength of anti-Stokes line, and that we found out to be 5416 angstrom. I hope this is clear to all of you. Then we'll proceed to ask the next question. The question says, for the exciting light of 4358 angstrom in the Raman spectrum of benzene shows Stokes line at 4477 angstrom. If the same benzene is irradiated with monochromatic light of 5461 angstrom, then find the wavelength of Stokes line in a Raman spectroscopy. So here this question is a bit different with respect to the previous question. In the previous question, the question was about calculating the anti-Stokes line, but here one incident light and the corresponding Stokes line is given, but here we want to find if there is another light of different frequency, a different wavelength is used, then what will be the wavelength of the Stokes line. So like the previous question, we first obtained the Raman shift in terms of wave number unit. So first in this question also we will obtain the Raman shift in wave number unit, and then using that wave number unit we will find out the wavelength of Stokes line in the second case. So options are option A 5369 angstrom, option B 5649 angstrom, option C 5829 angstrom, or option D 5979 angstrom. So here are the four options. Again, I'll give you a few minutes to try this question, and after some time we will discuss. So now let's solve this question. So like the previous question, first things the value of wavelengths are given, but we know the Raman shifts are in terms of wave number, so we need to convert wavelength to wave number. So the wave number corresponding to incident line will be 1 by lambda I, which is equals to 10 to the power 8, because Armstrong means center minus 8, so 1 by lambda will be 10 to the power 8, so it will be 10 to the power 8 divided by 4358, which will be 22,946 centimeter inverse. Similarly, if you consider the given Stokes line wavelength, so the wave number of the Stokes line will be 1 by lambda s, which will be 10 to the power 8 divided by 4477, and this is 22,336 centimeter inverse. Now, this two line difference will give us the Raman shift. So the Raman shift will be lambda I bar minus lambda s bar, which is 22,946 minus 22,336. So the difference is 610 centimeter inverse. So now in second case, since the same benzene is irradiated by another monochromatic light of different wavelength, since this Raman shift is a characteristic feature of a particular liquid, so if the same liquid is irradiated with different light, then the Raman shift will remain the same. So this is the Raman shift, and it is constant for a particular liquid. So in the second case, the incident light is, in the second case, the incident light, we have 1 by lambda I, which is 1 by 10 to the power 8 by 5461, which is 18,312 centimeter inverse. Now we know the wave number of Stokes line is less than the wave number of incident line, and it is smaller by the value of Raman shift. So the value of Stokes line will be the value of Stokes line will be minus delta nu bar is 8,312 minus 610 centimeter inverse, which is 17,702 centimeter inverse. Now, in order to convert it into wavelength, the wavelength of Stokes line is 1 by, it is 1 by 17,702 centimeter inverse. It will give you 5.649 into 10 to the power minus 5 centimeter. It will be 5,649 into 10 to the power minus 8 centimeter, or 5,649 angstrom. So this is the correct answer. The correct option will be 5,649, which is option B. So in this question, the question was for the exciting light wavelength was given and the Raman spectrum benzene showed the Stokes line. But if different frequency or different wavelength of exciting monochromatic light is irradiated, then what will be the value of the wavelength of Stokes line? So since the same liquid is being irradiated, so the shift in the Raman spectrum will be remaining the same. So in the first case, we will calculate the shift by subtracting the wave number of incident line and wave number of Stokes line. And then, since the incident line is given in the second case, we will again subtract the shift to get the value of the Stokes line that will appear in the second case, corresponding to the new monochromatic light of wavelength 5,461 angstrom. So, the correct option will be option B, which is 5,649 angstrom. Then, question number 3. Question says a substance shows a Raman line at 4,565 angstrom when excited with 4,350 angstrom. Deduce the position of Stokes and anti-Stokes lines for the same substance when the exciting line is 4,045 angstrom is used. So this question is pretty much similar to the previous question, but in previous question there we needed to calculate only the Stokes line, but here we need to calculate both the Stokes line and anti-Stokes line. So these are the 4 options. Since we have to calculate both Stokes line and anti-Stokes line, so in each option there is 2 wavelength values. Option A 5,333.2 angstrom, 4,221.6 angstrom. Option B is 6,732.8 angstrom and 5,832.8 angstrom, 4,222.6 angstrom, 3,881.7 angstrom, 4,756.7 angstrom, and 3,472.6 angstrom. So these are the 4 options. I'll give you a few minutes to try this question. Then after some time, I will discuss. So similar to the last question, again we will find the corresponding wave number corresponding to the when we will find first the wave number corresponding to the exciting line and the Raman line. So in first case, the exciting line wave number will be 1 by 4350 Armstrong, which is 10 to the power 8 divided by 4350 centimeter inverse, which is 22,946 centimeter inverse. Now, the Raman line, whether this is Stokes line or anti-Stokes line, we don't know. So we simply write it as nu r prime, nu r bar, which will be 1 by 4,565 Armstrong, which is 10 to the power 8 divided by 4565, which is equals to 2190 21,906 centimeter inverse. Now you see the wave number of incident light is greater than the wave number of Raman line. So according to the previous discussions, this line will be the Stokes line, because in Raman spectra, first Stokes lines appear, then the relay line or the incident line, and then anti-Stokes line, where this is the centimeter inverse or 1 by lambda units. So this is the Stokes line. So now how will find the Raman shift? The Raman shift will be delta nu bar, which will be equals to 12,946 minus 12,100, sorry, 22,946, 21,906 centimeter inverse, which is 1,040 centimeter inverse. Now, this is the Raman shift. Then the question was, if the new exciting line wavelength is 4,045 Armstrong, then what will be the Stokes and anti-Stokes line? So this is the Raman shift we obtained. Then in the second case, the incident light wave number will be 1 by lambda I, which will be 1 by 4,045 Armstrong. This is 10 to the power 8 divided by 4,045 centimeter inverse, which is 24,722 centimeter inverse. Now, the delta nu we know, then Stokes line will be nu I minus delta nu, and anti-Stokes line will be nu I plus delta nu bar. So it will be 24,722 minus 1040 centimeter inverse, or 24,722 minus or plus 1040 centimeter inverse. Now, for Stokes line, the wave number is 23,682 centimeter inverse, and for anti-Stokes line, it is 24,000 plus 1040, so it is 25,762 centimeter inverse. Now, the wavelength of Stokes line will be 1 by nu s bar, which will be 4,222.6 Armstrong, and the
wavelength of anti-Stokes line will be 1 by new anti-Stokes bar, which will be 3881.7 angstrom. So these are the two values. So the correct option will be option C, 4222.6 angstrom and 3881.7 angstrom. So this question is pretty much similar to the previous question, but here we calculated both the Stokes line and anti-Stokes line. So I hope this is clear to you. Then coming back to the coming forward to the fourth question. The question says in the pure rotational Raman spectrum of HCl molecule, the displacement of the Raman shift from the exciting line are represented by del nu bar equals to plus minus 24J plus 36 centimeter inverse. Calculate the moment of inertia of HCl molecule with, you can take the value of Planck's constant as 6.63 and 10 to the power minus 34 joule into second. Now the options are option A 4.66 into 10 to the power minus 47 kg meter square. Option B 5.17 into 10 to the power minus 45. Option C 6.27 into 10 to the power minus 43. And option D 7.78 into 10 to the power minus 40. All the units are kg into meter square because we need to find out the value of moment of inertia, and we know the units of moment of inertia is mass into distance square, which is kg into meter square. So all these are in SI units. So now what the question said, in case of pure rotational Raman spectrum, so in the previous three questions we solved, we were only talking about the Raman spectrum, whether this is rotational or vibrational, we had not considered. But here it is the case of pure rotational Raman spectrum, and the Raman shift is given in terms of J values, because we know J are the rotational quantum numbers. So corresponding to the J values of the transitions or the transition or the levels that are involved in the transition, the shift in from the Raman shift from the exciting lines are del nu bar is equal to plus minus 24J plus 36. Then how we will calculate the moment of inertia? So there is a particular formula which we will use, or we will compare the formula with the given formula, and from that we will find out whether this transition corresponds to Stokes line or anti-Stokes line or whatever it may be. Then from that particular value we will found the moment of inertia. So I will give you a few minutes to try this question. This is a very interesting question. We will definitely solve it and we will find out how we can approach this type of question. So take your time, a few minutes. Then after some time I will discuss.
I request you to mute yourself. So we will solve the fourth question. So we have already in this session, I have already solved three questions. No, so now coming to the fourth question. So this question was related to pure rotational Raman spectrum of HCl molecule. Now the question says that the Raman spectrum of HCl molecule shows the Raman shift from the exciting line, which is represented by the formula del nu bar equals to plus minus 24J plus 36 centimeter inverse. Calculate the moment of inertia of HCl molecule, and these are the options that were given. Now, if you talk about the pure rotational spectra of Raman spectrum, then according to the or corresponding to the selection of the Raman spectrum, selection rule of the Raman spectrum, the selection rule for Raman spectrum is delta J is equals to plus minus 2. So, when either there is transition from 0 to 2 or there is transition from 2 to 0. So, corresponding to each transition, or whether the or in general, we can say that the transition can occur from J to J plus 2 or J to J minus 2. So there are two types of transition. So now you need to find out whether this transition corresponds to J to J plus 2 or J to J minus 2. So now if you consider the transition from J to J plus 2, so we already know there is a expression for transition from J to J plus 2. So in case of Raman spectrum, how the transition yield the result. So we will find, suppose the transition occurs from J to J prime, then according to rotational spectra, we have already discussed, we know EJ is given by J into J plus 1, BHC, where B is the rotational constant. So now if the transition occurs from J to J prime, then from this we can calculate EJ by HC will be J into J plus 1 B. So E by S is nothing but the wave number. So this wave number nu bar is J into J plus 1 into B. So now similarly here, if the transition occurs from J to J prime, then nu bar will be E J prime minus EJ divided by HC. So suppose the transition occurs from J to J plus 2, then what will happen? Nu bar will be J plus J into J plus 1. So J here, the final J prime is the final state, J is the initial state. So here J plus 2 is the final state, J is the initial state. Then energy of final state minus energy of initial state. So for J plus 2, we will take it at J. It will be J plus 2 into J plus 2 plus 1. So it is J plus 3 minus J into J plus 1. And in common, it will be B. So if you calculate it, it will be J square plus 3J plus 2J plus 6 minus J square minus J into B, which will give mu bar equals to, so J square J square will get cancelled out. It will be 5J 5J minus J 4J plus 6. So it will be 4J plus 6 into B. So if you take 4 common or 4B common, it will be J plus 3 by 2. So if you compare
this equation to the given expression 24J plus 36. So you see, we can compare these two relations because there is a positive sign in both cases. So we can say 4BJ plus 6B is equals to 24J plus 36. 24J plus 36. So in both cases, if you compare, you can easily get the value of B. So 6B equals to 36 and B equals to 36 by 6, that is 6 centimeter inverse. Now, according to the question, we need to find out the value of moment of inertia. And we know in case of B, the expression of B is given by, that is the rotational constant, h by 8 pi square I c, is not it? Because in case of rotational spectra, we have already discussed the expression of rotational constant, which is h by 8 pi square I c. So from this, I will be h by 8 pi square b into c. So now, what will be the value of I? I will be value of h. H is 6.62 or 63 into 10 to the power minus 34 divided by 8 into 3.142 square into value of b is 6 centimeters. So it will be 6 into 10 to the power 2 meter, because when you convert centimeter inverse to meter inverse, you multiply it by 10 to the power 2. So it will be 6 into 10 to the power 2. Then velocity of light 3 into 10 to the power 8 meter per second. So if you calculate, the value of I will come out to be 4.66 into 10 to the power minus 47 kg into meter square. So if you see the options, the correct option will be option A, 4.66 into 10 to the power minus 47 kg into meter square. So Priyanka, do you have any doubt corresponding to this particular question?
No, I have some doubt. In assignment 12, in question number 3, option B and C both are the same.
Sorry,
This
once
is from
again.
the assignment number 12. From
So
in
actually,
assignment.
Priyanka, I don't deal with the assignments. I
Okay,
generally, what I do as a PMRT of this course, I solve the previous year questions or some sample questions, which will be covering
okay,
the current
okay.
week lectures.
So,
So,
can you tell me to which person I should mail regarding this error?
so I think corresponding to each course, there is a discussion forum in that particular course. So in that discussion forum, you can post your doubts, and there are
Okay,
dedicated um, TAs who will respond to your queries.
okay, okay. In assignment 7, if also there is a doubt.
So you can do the same thing, whatever your doubt may be. You can go
Okay,
to the discussion forum for a particular course, and then to that discussion forum, it is basically like a uh, interactive chatting section, you may say. So there you post your queries, then correspond to each query, you will be getting the replies. So I will advise you to solve your
okay,
queries through the discussion forum only.
okay, okay. Thank you, sir.
So again, do you have any problems to this particular question?
No, no, not at all. No, no.
Okay. Okay. So we will proceed towards the next question, the fifth question. The question says the values of vibrational wave number, which is omega e bar, and the unharmonicity constant, which is omega e bar xc, are 1580.6 and 12.06 centimeter inverse, respectively. For the ground state of oxygen, then calculate the 0 point energy of oxygen molecule. The value of Planck's constant H is also given. The options are option A, 1.566 into 10 to the power minus 20 joule. Option B, 2.166 into 10 to the power minus 16 joule. Option C, 3.472 into 10 to the power minus 12 joule. And option D, 4.219 into 10 to the power minus 10 joule. So these are the four options. I'll give you a few minutes to try this question. So if you remember the energy expression for vibrational levels of an anharmonic oscillator, then the expression for energy of corresponding to a particular vibration level V was Hc omega E bar plus half minus omega E bar Hc V plus half square. So this is the expression corresponding to a particular value of V. Now here the question says calculate the 0 point energy of oxygen molecule. Now for 0 point energy, you know, for 0 point energy, the value of vibrational quantum number V is 0. Then if you put the value of V equal to 0, so E0 will be Hc omega E bar into half minus omega E bar Hc into 1/4, that is square of half. So you have all the given values. It is 6.63 into 10 to the power minus 34 into 3 into 10 to the power 8. Then omega is also given. Omega is 1580. Since all these are in SI units, so we will convert it to meter inverse. So 1580.6 into 10 to the power 2. So it will be 158060 into 1/2 minus 158060 into xc. Xc is again 1206 divided by 4. So sorry, this term will not be here. So the term corresponding to omega exc is 12.06 centimeter inverse. So if you calculate, you will get the value of 0 point energy is E0, which is 1.566 into 10 to the power minus 20 joule. So this is the answer, and it corresponds to the option 1.56 into 10 minus 20 joule, that is option A. So this was a pretty simpler question. So we need to simply use the expression for uh, anharmonic oscillator corresponding to a particular level. We have the expression which is Hc omega E V plus half minus Xc omega E V plus half square. So for calculating 0 point energy, we know the value of lowest level is V equals to 0. Then if you put the values, you will get the 0 point energy is 1.566 into 10 to the power minus 20 joule. So the correct option is option A. Now, coming to the sixth question. The question says the values of vibrational wave number omega E and anharmonicity constant omega Ex are. So again, the question number 6 was. So question number 6 and question number 7, both questions have similar parameters or same value of the parameters. So the question is again, the vibrational wave number omega I and the unharmoniously constant omega Ex are 1580.6 and 12.06 centimeter inverse respectively for ground state of oxygen. Then calculate the vibrational Raman shift when the transition to be occurred from vibrational quantum number V to 0 to V equals to 1. So in the first case, in the previous question, we discussed about how to calculate the energy for a particular level. Now here, this question says we will calculate the shift in the vibrational Raman shift when the transition occurs from the vibration quantum number from V equal to 0 to V equal to 1. So we will consider here two levels. So new V prime is 1 and V is 0. So the options are option A, 1466.82 centimeter inverse, option B, 1556.48 centimeter inverse, option C, 1644.72 centimeter inverse, and option D, 1772.39 centimeter inverse. So these are the four options. I'll give you a few minutes to try this question. Then after some time, I'll discuss. So now, if you talk about the vibration Raman shift, then the vibrational Raman shift is given by the new bar will be E1 minus E0 by Fc. Now, what is E1? E1 is Fc omega E 1 plus half minus omega E bar Fc 1 plus half square. E0 is Fc omega E bar 0 plus half minus omega E Fc 1 0 plus half square. So if you put all the values, because you know all the values, this so the Raman shift will be given by omega E. So SC will be getting cancelled out because you see In the numerator, there is SC in common, and in the denominator, there is SC. So both these SC will be getting cancelled out. So we will be putting omega e, it is 1 plus half, so it is 3 by 2 minus omega e xc, omega e bar xc, 3 by 2 square is 9 by 4, then minus, this is omega e by 2, then plus omega e bar xc 1 by 4. So if you put this, if you calculate, again, it will be a simpler value. So del nu bar corresponding to transition from 0 to 1, it will give omega e bar, because 3 by 2 omega e minus 1 by 2 omega, it is omega e minus 2 omega e xc. So it will be 1580.6 minus 12.06 into 2 centimeter inverse, which is 1556.48 centimeter inverse. So this is the answer. And if you see the options, this is 1556.48 centimeter inverse. So the correct answer is option B. So this question was to find out the vibrational Raman shift between the two levels. And for two levels, the vibrational wave number and the unharmonic constant value was given. So the two levels was also given, V equal to 0 to V equal to 1. So if you put all the given value, you can easily get the value of Raman shift, which is 1556.48 centimeter inverse. So coming to the next question, question number 7. The question says, in the vibrational Raman spectrum of HF, the Raman lines are observed at wavelength 2675 Armstrong and 3435 Armstrong. Consider Raman lines to appear at distances from the exciting line corresponding to each by active fundamental vibration. Find the fundamental vibrational frequency of the molecule. The options are option A 1.24 into 10 to the power 14 Hz, option B 1.38 into 10 to the power 14 Hz, option C is 1.48, and option D is 1.68. So here are the four options. The question says, in case of vibrational Raman spectrum, the Raman lines are observed at wavelength 2675 Armstrong and 3435 Armstrong. Then one corresponding to each by active fundamental vibration. Then find the fundamental vibration frequency of the molecule. So how we will approach this question? So I'll give you a few minutes to try this question. Then after some time, I will discuss. So now let's solve the second question. So the two lines are observed and they are at wavelength 2675 angstrom. So two Raman lines are observed, one at wavelength 2675 angstrom and other is 3435 angstrom. So now, like to the previous questions, the same approach we will make here. We will first calculate the wave number corresponding to this particular values, and then we will find the value that we need to find out the value of frequency. So here the Raman lines are observed at wavelength 2675 angstrom and 3435 angstrom. So the first line, suppose this is first line, it will be 1 by 2675 angstrom, which is 10 to the power 8 divided by 2675 centimeter inverse, which is 37383.2 centimeter inverse. And for second line, it is 1 by 3435 angstrom, which is 10 to the power 8 divided by 3435, that is 29112 centimeter inverse. So now you see, consider Raman lines to acquire a distance from the exciting lines corresponding to each by an active fundamental vibration. Now you see the two wavelengths that are given, they don't correspond to the exciting levels, they correspond to the Raman lines. So how we will obtain the Raman shift from these two exciting lines or two Raman's lines? So we know one line appears at, suppose this is the exciting line, then one line will appear at nu 0 bar plus delta nu and other line will appear at nu 0 bar minus delta nu. So how we will calculate delta nu? So delta nu will be mu 0 bar plus delta nu minus mu 0 bar minus delta nu divided by 2. So mu 0 bar plus delta nu is 37,383.2 centimeter inverse, and mu 0 bar plus, sorry, mu 0 bar minus delta nu bar is 29,112 centimeter inverse. Now these are the two values we get. Then we need to find the value of Raman shift. So the value of Raman shift del nu bar will be 37383.2 minus 29112 by 2. This value will be 4136.6 centimeter inverse. So this 4135.6 centimeter inverse corresponds to the fundamental vibration. So now this is the wave number corresponding to fundamental vibration. Wave number corresponding to fundamental vibration. Now the frequency of vibration will be how much? It will be C into wave number corresponding to fundamental vibration. So it will be 3 into 10 to the power 10 into 4136.6. So here 3 into 10 to the power 8 is the value of c, that is velocity of light, and 4136.6 centimeter inverse into 10 to the power 2 is meter inverse, so it will be per second. So it is 1.24 into 10 to the power 14 per second, which is hertz. So this is the answer. So the correct answer is option A, 1.24 into 10 to the power 14 hertz. So this question was about finding the fundamental vibrational frequency. So now the question says there are two Raman lines that are observed corresponding to different wavelengths, and it is given that consider Raman lines to appear at distances from the exciting line corresponding to each by active fundamental vibration. So the difference between the two position, that is exciting line and Raman line, correspond to fundamental vibration. So first we obtain the wave number corresponding to these two wavelengths. Then from this wave number we know that the two lines that appear, one is higher and another is lower wave number. So if you want to calculate the value of Raman shift, so it will be higher minus lower divided by 2, because the formula is like this. So from the expression we can obtain this. So if you calculate, it will give the wave number which corresponds to the fundamental vibration. So since the wave number is given, we know the value of frequency will be velocity into wave number. So the value of c we put here 320 meter per second. Then in order to convert centimeter to centimeter inverse to meter inverse, we will multiply it 10 to the power 2. So the correct answer will be 1.24 into 10 to the power 14 hertz. Now coming to the eighth question, the question says rotational constant of HM molecule is B, which is 21 centimeter inverse. Calculate the wavelengths of first two anti-Stokes lines that are observed in pure rotational Raman spectrum when HF molecule is irradiated with 405 nanometer mercury line. The options are option A 402.9, 401.6, option B 406.8, 409.7, option C 410.9, 415.6, option D 421.8 and 418.5. So these are the four options. The value of rotational constant of HF molecule is given. So we need to find out the wavelength of first two anti-Stokes lines. And the lines are appearing when the HF molecule is irradiated with the mercury line of wavelength 405 nanometer. So I'll give a few minutes to try this question. Then after some time, I'll discuss how we will solve this question. So how we will approach this particular question. So now, if you remember, in the beginning of the session, I had discussed this. So in case of Raman spectra, the central line, that is the exciting line, that occurs at 0, then the anti-Stokes line occurs at 6b, 10b to 14b like that, and the Stokes line occurs at minus 6b, minus 10b like that. So here, if you compare this particular situation, then you can see in this question the exciting line is given. So the exciting line, that is the incident line, wave number will be 1 by 405 nanometer, which is 10 to the power 9 divided by 405 nanometer. So which will give 2469135.8 meter inverse. So this is the wave number of exciting light, that is with whom the HF molecule is being irradiated. Now, if you see, the value of B is given. The value of B is 21 centimeter inverse, so it will be 2100 meter inverse. Now, this line corresponds to nu zero at the zero position. Then the two anti-Stokes line, one line will appear at 6b and another line will appear at 10b. So how these 6b and 10b is appearing? So if you see, we had already discussed the expression for Raman spectrum. When the transition occurs from J to J plus 2, the general expression for Raman shift is given by 4b J plus 3 by 2. If you remember, we had already discussed about it. Then here, the two Raman spectrum that arises, one is J0 to J2, another is J1 to J3. These are the anti-Stokes lines. They correspond to transition from J0 to J2 and J1 to J3. So now, for line corresponding to 0 to 2, we will get 6b. So 6 into 2100, which is 12600 meter inverse. Then 1 to 3 is 10b, 10 into 2100, which is 21000 meter inverse. So one line will be nu 0 bar plus 60, another line will be nu 0 bar plus 10b. So nu 0 bar plus 6b means it is 2469135.8 plus 12,600 meter inverse, which is again is 2469135.8 plus 21,000 meter inverse. So this will be in terms of meter inverse. Now the question says we need to find out the wavelengths. So the wavelengths corresponding to these two lines will be, so will be 1 by mu 1, another will be 1 by mu 2 or nu bar 2. So one line will correspond to 402.9 nanometer, and another will be 401.6 nanometer. So if you see, they are placed at a distance 12,600 meter inverse, 12 or 21,000 meter inverse. But if you compare the distances in terms of wave number, it is only point. It is only 1.3 nanometer separation. So generally, all the spectrums which are studied are given in terms of meter inverse or the wave number units because they are easily distinguishable in this particular system of units. So if you see the correct answer will be option A 402.9 meter and sorry, option A is 402.9 nanometer and 401.6 nanometer. So these are so this is the correct option, that is option A. Now coming to the next question, question number 9. The question says, if HCl molecule is irradiated with 404.7 nanometer mercury line, then calculate the wavelength of first two Stokes line observed in the rotational Raman spectrum, where the rotational constant of HCl molecule is given as 10.65 centimeter inverse. And the given options are option A 305.7 nanometer, 306.4 nanometer, option B 405.7, 406.4, option C 405.5, 506.7, option D 605.4 and 606.5. So here are the four options. This question is pretty much similar to the previous one. So here we will calculate the first two Stokes lines. In the previous question, we were calculating the first two anti-Stokes lines. Here we will calculate the first two Stokes lines. So I'll give you a few minutes to try this question. Then after some time, I will discuss. Okay, so how we will solve this question? These are pretty much similar to the previous question. So in the previous question, it was 0, then plus 6b plus 10b. So here it will be minus 6b minus 10b. So first we need to find out the value of this new 0. So here b is given 10.65 centimeter inverse, so which is 1065 meter inverse. Now corresponding to the incident light of wavelength 404.7 nanometer, its wave number will be 1 by lambda, which will be 1 by 404.7 into 10 to the power minus 9 meter inverse. If you calculate, it will give us 2470966.15 meter inverse. Now, one value will be 2. So, we have B is 1065 meter inverse, 6B 6 into 1065, which is 6390 meter inverse. 10B is 10 into 1065, which is 10650 meter inverse. So one line will be mu 0 bar minus 6B, which is 2470966.15 minus 6390, which is 2464576.15 meter inverse. Then the next line will be 5 minus 10D, which will be 2470966.15 minus 10650, which is 2460316.15 meter inverse. Now we need to convert it into wavelength units, that is nanometer or angstrom. Then these two line will correspond to, so 1 by nu 1 bar will give you lambda 1, which will be 405.7 nanometer. Then 1 by nu 2 bar equals to lambda 2, which is 406.4 nanometer. So this is the answer. Now if you see, the correct option will be option B, 405.7 nanometer, 406.4 nanometer. So now let's go to the last question. The question said, when HCl molecule is irradiated with 436 nanometer of mercury line, the Stokes line that has been observed at 20057 centimeter inverse, calculate the force constant of HCl molecule corresponding to the fundamental vibrational frequency. Reduced mass of HCl molecule is 1.62 into 10 to the minus 27 kg. The options are option A, 476.98 Newton per meter, 459.28 Newton per meter, 438.27 Newton per meter, and 227.72 Newton per meter. So these are the four options. I'll give you a few minutes to try this question, and after some time I will discuss. So now the like to the previous question, first we will calculate the wave number corresponding to the incident radiation. So the wave number corresponding to incident radiation is 1 by lambda I, which is 1 by 436 into 10 to the power minus 9 meter inverse, which is 2293578 meter inverse. Now the Stokes lines is given. The Stokes line wave number is 20057 centimeter inverse, which is equal to 2005700 meter inverse. Now the Raman shift will be given by mu I bar minus mu s bar, which is 2293578 minus 2005700, which is 287878 meter inverse. Now this Raman shift corresponds to the fundamental frequency of vibration. So the fundamental frequency will be this Raman shift into velocity of light. It is 2877878 into 3 into 10 to the power 8. It is 8.636 into 10 to the power 13 hertz. Now we know omega is equal to k by mu root over then 1 by 2 pi k by mu root over equals to f. So k will be 4 pi square f square mu. So the value of k will be 4 into pi is 3.142 square into f square. F is 1. That is the value of mu. We can write the value of mu was given 1.62 into 10 to the power 27 kg. 1.62 into 10 to the power minus 27 kg into the value of f, which is 8.636 into 10 to the power 13 square. So if you multiply all this quantity, it will give you 476.98 Newton per meter. So the value of force constant for this particular vibration is 476.98 Newton per meter. The correct option is option A, 476.98 Newton per meter. So this question was about finding out the value of force constant of HCl molecule. The molecule was irradiated with a radiation of wavelength 436 nanometer of mercury line. So corresponding to that particular wavelength, we first calculated the wave number. Now the wave number, since the wave number we have obtained, then the value of Stokes line is also given at 20057 centimeter inverse. Then we again converted into meter inverse. So from both these values, we can calculate easily the Raman shift. Then after calculating the Raman shift, this Raman shift corresponds to the fundamental vibration, and this vibration will, so using the value of Raman shift, we can easily calculate the fundamental vibration frequency. So once we calculate the fundamental vibration frequency, from the vibration frequency we have the formula. Angular frequency is omega, which is k by mu. So omega is 2 pi f, which is k by mu root over. So if you take 2 pi to the right hand side, it will give us 1 by 2 pi k by mu root over is equal to f. So k will be 4 pi square f square into mu, where mu is the reduced mass, f is the fundamental frequency of vibration. So since we have all the values, so when you put all the values, you can easily get the answer. So the correct option is 476.98 Newton per meter. That is option A. I hope this is clear to everyone. So with this, we have come to the end of the 12th interaction session. So in the next interaction session, basically, which will be occurring, I think, on Tuesday, that is on 16th April. So during that session, I will basically revise the whole atomic and molecular physics course, what we have discussed in this course. So with this, we have come to the end of this today's interaction session. Thank you.